Alright, so hello everyone. This is the lecture on capacitance. In this lecture, we are going to study about electrostatic field, working of capacitors, capacitance, which is the ability of your capacitor to store charges, and capacitors in series and parallel, and the factors affecting the capacitance. So let's start. The first topic which we are going to study is about electric field. So if we have two conducting plates such as shown in the first figure, and if they are connected to a voltage source, conducting plates. So as a result of connecting it to a voltage source, what would happen is, let's say if we have connected the positive terminal to the top plate and the negative terminal to the bottom plate. So as a result of this, what will happen is the top plate will accumulate some positive charges on it, and the bottom plate, which is connected to the negative terminal of the battery, it will accumulate some negative charges on it. Now because of this, and since it has a distance, these two conducting plates, they are separated by a distance. As a result of this, what will happen is it will have some electrostatic force or electrostatic field between the two plates. Now what would happen is, if we place any charge, let's say if we are placing a electron, which is a negatively charged particle, in this electric field, so what would happen is this electron will get attracted towards the positively charged plate, and if we place a positive charge, that is a proton, in this field or in this electric field, this will get, the proton will get attracted towards the negatively charged plate, right? So any region between two plates in which an electric charge experiences a force, it is called as electrostatic field. And the strength of this electrostatic field, or as we call it simply as electric field, so the strength of this electric field is called as electric field strength, and it is denoted by capital letter E. So this electric field E, electric field strength E, it will depend on two factors. The first one is the supply voltage, and the second factor on which this electric field strength would depend on is the distance between the two plates, right? So electric field strength E is directly proportional to the supply voltage. That means the more voltage you give across this plate, the higher will be the electric field strength, and it is inversely proportional to the distance. That is, if you reduce the distance between the two plates, the electric field strength would again increase. So we have developed a formula for calculating electric field strength, which is E, that is your electric field strength, is equal to the supply voltage divided by the distance between the two parallel plates. Now capacitors, they have quite a similar type of a structure. So they include conducting plates which are separated by a dielectric medium between them. So dielectric medium, they are essentially insulating material, and as we all know that the insulating material, they are poor conductor of electric current, right? So this is the basic construction of a capacitor. You have two conducting plates which are separated by a dielectric medium in between, And the symbol of this capacitor is given by this symbol here, right, where the two parallel lines, they denote the two parallel plates of your capacitor. Now let's understand the working of capacitor. So when we take a capacitor which is still not connected to a voltage source, right, we have just taken a capacitor. So initially this capacitor, the plates of the two parallel plates of this capacitor are electrically neutral. Electrically neutral means the number of positive charges and the number of negative charges on the two plates will be equal, right? Now when we connect this capacitor to a voltage source, in that case what would happen? Let's say we have connected the positive terminal of the battery to the top plate and the negative terminal of the battery to the bottom plate. So in that case what will happen is the electrons will get attracted towards the positive terminal and they will start flowing towards the positive terminal of the battery. Similarly, from the negative terminal of the battery, some electrons will start flowing towards the bottom plate, right? However, if you note that between the two plates we have a dielectric medium, which is an insulator or a poor conductor of electricity. So in that case what will happen is the electrons which has traveled from the negative terminal of the battery all the way to the bottom plate, it won't be able to cross this barrier because in between the two plates you have a poor conductor of electricity, right? So as a result the electrons, they will start accumulating at the bottom plate and the electrons from the top plate will continue to flow towards the positive terminal of the battery. So at the bottom plate you will have higher concentration of electrons and at the top plate there will be a deficiency of electrons. That means there will be more of positive charges on the top plate. Okay. Now, so this thing has been demonstrated in this figure. So the top plate, it accumulated all the positive charges, or there is a deficiency of electrons, and at the bottom plate you have abundance of electrons, or the concentration of electrons are more at the bottom plate. So as we have discussed just now, because of this difference in the charge or accumulation of positive and negative charges across the two plates, it will result in a electric field between the two plates. Okay. So as we can see here, the capacitor has the capability of storing charges in form of electric field. Right? So capacitor, it acts like a small battery which stores some charges. Right? Now, one of the questions that may arise is, why do we need such kind of a small battery in our circuits? Why can't we use a battery which continuously provides the charge or the energy which our circuit needs? Now I would like to give you an example to clarify that. So essentially, let's say if we are driving on the road and the car, it suddenly breaks down in the middle of the road. What we would do is we would get out of the car and try to push it onto the side of the road. Right? So when we are pushing the car onto the side, when we start to push the car, um, we require more force to move the car. But once the car starts rolling, um, the amount of force which we need is less in comparison to when we started pushing the car, right? So in some applications, something like in motors, electrical motors or fans, right? So they need a extra amount of energy to start rotating, right? Something like in a ceiling fan, when you turn on the power supply to the motor, which is connected to the fan, uh, it requires a little bit extra amount of energy. And to provide that extra amount of energy for that instance of time or just to get it started, we use a capacitor. And such type of motors, they are called as capacitor start, capacitor run motor, right? So once the motor starts rotating, the supply energy is sufficient to maintain that rotation. But to initiate that rotation, we need a little bit of kick or a start to uh, to start the rotation, right? So capacitors, they provide that extra bit of energy which our circuit needs to maybe to start the flow of electrons or to start the rotation of motors, right? Now the next thing is about capacitances. So as I mentioned, capacitance is the ability of your capacitor to store charges, right? It is denoted by capital letter C. And capacitance, it again it depends on two factors. It depends on the charge which the two plates they are holding, and the voltage, the supply voltage, right? So capacitance, it is directly proportional to the charge between the two plates. So the more the charge, the larger will be the capacitance or its ability to store charge, right? And it is inversely proportional to the supply voltage. Okay. So capacitance altogether, if we develop a formula, it is given by Q, which is charge divided by the supply voltage. Now capacitance, it is measured in farads, right? In short, we write it as capital letter F. And generally, we have some smaller value of capacitances. I mean, they are more practical, right? Otherwise, in farads itself is a very large unit, right? So therefore, we use smaller units of capacitance, such as millifarads, microfarads, even nano and picofarads are quite popular or quite frequently used capacitances, right? So these are the conversion for uh, for the unit. Now, for example, if we have to convert 1 millifarads into microfarads, so from millifarads, if we are moving down to microfarads, we divide it by 1000, right? So 1 millifarads will be equal to 1 divided by 1000, or we can say 10 to the power minus 3 microfarads. And similarly, in the next example, we have to convert 1 microfarads to millifarads, the other way around. So if we are going from bottom to the top, we multiply by 1000. So 1 microfarad will be equal to uh, 10 to the power 3 or 1000 millifarads. Okay. Now, based on the formula which we have discussed, let's take an example. So in the first problem, we have to determine the potential difference across a 4 microfarad capacitor. So the value of capacitance is given. So our capacitor, it can hold 4 microfarad of charge. Now when charged with 5 millicoulombs, so the charge on the capacitor is given 5 millicoulombs. Now the capacitance is given in microfarads and the charge is in millifarads. So obviously the first step would be to convert the units. Now let's have a look at the solution. So as I mentioned, we have to convert the units. So I've converted 4 microfarads into farads, the SI unit. So I multiplied it by 10 to the power minus 6. And similarly, charge was given as 5 millicoulombs and I have converted it into coulombs by multiplying it with 10 to the power minus 3. Okay. Now I already have the formula or the relation between charge, capacitor and the supply voltage. I have to determine the potential difference or the voltage which should be applied across the capacitor plates. Okay. So this voltage I need to identify. So if we modify this formula and change it to find the value of potential difference or the voltage, so V will be is equal to charge divided by the capacitance C. Okay, all the values are given. We have already done the unit conversion, so I have substituted them and done the calculation. So after calculation we'll get 1250 volts, or we can say 1.25 kilovolts. Let's take another example on the same formula. So in this problem we have to find the charge on 50 picofarads of capacitor. So the capacitance is given as 50 picofarads. When the voltage applied, so this time in this problem the voltage is given, it is given to be 2 kilovolts, and we have to find the charge, right? We have to find Q. So again the first step would be to convert the unit and then use the formula properly or appropriately and do the calculations correctly to get the value of charge. So let's look at the solution of this. So charge, it is given as 50 picofarads, so I have converted it into farads by multiplying with 10 to the power minus 12, and the voltage it was given as 2 kilovolts. So again I have converted it into volts by multiplying it with 10 to the power 3. Now again using the formula appropriately, so I have the formula, or you can say the relation between capacitance, charge and the supply voltage. So I have modified this formula to find the value of charge. So charge Q will be equal to the capacitance multiplied by voltage. Okay. We have already found the values, done the unit conversion. So let's substitute the value of charge and the voltage in the equation. So if we put them in the equation and carry out the calculations correctly, we'll end up getting 0.1 multiplied by 10 to the power minus 6 coulombs. And we know 10 to the power minus 6 coulomb is 1 microcoulombs. So essentially we can say it is 0.1 microcoulombs of charge. Okay. Now moving on to the next topic in this lecture, we have to study about capacitors in series and capacitors in parallel. So when the capacitors, they are connected in series, it is given by or the equivalent capacitance C we can find by using this formula. Now this formula, it comes from the Kirchhoff voltage law, which says that the supply voltage Vs will be equal to the voltage drop across each of the elements in the electrical circuit. So the voltage drop across the first component or the first capacitor C1 is V1, and the voltage drop across the second capacitor is V2. Okay. And we have just now studied the formula C is equal to Q divided by V, or we can develop a formula to find the value of voltage, which is V is equal to charge divided by capacitor. Now the charge or the current flowing across or between the two capacitors C1 and C2 will be the same as your supply charge or the charge generated by your supply voltage. Okay, since they are connected in series. Since the two capacitors, they are connected in series, the charge flowing through them will be the same. Okay, so using this formula, if I calculate the value of supply voltage, it will be charge divided by the total capacitance or the equivalent capacitance. So let's say the equivalent or the total capacitance is C. Okay, so it will be charge Q divided by the total capacitance or the equivalent capacitance. Okay, and V1. So through V1, the charge which is flowing is Q, and the capacitance is C1. Similarly, V2 is again through capacitor C2. The charge which is flowing is Q, and divided by the capacitance is C2, right? So these Q's, they will get cancelled, and ultimately will end up getting 1 divided by C is equal to 1 divided by C1 plus 1 divided by C2. So this is the equivalent capacitance of two capacitors connected in series, two or more capacitors connected in series. So if you have more capacitor, let's say if you have another capacitor here, C3, you will add another 1 divided by C3. Okay, and you can continue adding depending on the number of capacitors you have in your circuit which are connected in series. Now again, using KCL, which is your Kirchhoff current law, which says now first thing we should know is current is the rate of flow of charge, that is Q divided by T. So let's say at T equals to 1 second, right, Q charge is flowing, right? So we are only considering this circuit at T equals to 1 second. So some charge Q is coming out from the supply voltage, and at this junction it is getting divided between the two branches. Let's say Q1 is flowing through C1, and the remaining charge Q2 is flowing through C2, like that. Okay, and then at this junction again they are combining. Q2 is coming from the top, and Q1 is coming from this branch. Okay, and they combine together at this point or at this junction, Q1 plus Q2, and finally Q charge is flowing back to the negative terminal of the battery. So according to Kirchhoff current law, the charge which is flowing into the junction and the charge coming out from the junction, or the current coming out from the junction, essentially if we are considering at a particular time, current and charge, they are equal, or they are directly proportional. So we can say that the charge Q is equal to Q1 plus Q2 according to Kirchhoff current law. Okay. Now from this formula again, if we develop another formula for Q, so Q is equal to capacitance C multiplied by the voltage. Okay. Now as we know that the voltage across the parallel connected components, they are same. So the voltage across C1 will be equal to your supply voltage, and the voltage drop or the voltage appearing across C1 will also be your supply voltage. Okay. So let's substitute the value in this equation, in the first equation. So C, let's say the total capacitance of the parallel connected circuit is C, and the supply voltage is Vs. Now Q1, to calculate Q1, again I am using this formula. So it is C1 multiplied by the supply voltage, and Q2 will be capacitance C2 multiplied by the supply voltage Vs. So Vs will get cancelled, or if we take Vs common from the term on the right hand side, so they will get cancelled each other, and finally we will be left with this formula here. So capacitor in parallel, so if we have two or more capacitors which are connected in parallel, the equivalent or the total capacitance C is equal to the sum of their individual capacitances, that is C1 plus C2. So again, if you have more than two number of capacitors connected, you can continue adding their individual capacitances like that. Okay. Now one thing to note here is capacitors, they are connected in series, they have this formula, whereas for resistances connected in series, if you remember, resistance in series, they had this formula, R1 plus R2 plus so on like that. And for capacitors in parallel, they are given by this formula, that is the sum of their individual capacitances, right? And resistances in parallel, they were given by this formula, right? So one thing to note here is the formulas, they are just the opposite, the formulas which are for resistance in parallel, they are just opposite of the of the capacitance formula which we have just discussed. Okay, so don't get confused with this. Now, having studied the formula, let's take a question. So in this first question, we are given with a network of parallel connected capacitors. We have three capacitors here of 125 microfarads, 200 microfarads and 50 microfarads. And we know the formula, or we have just now seen the formula for calculating the equivalent or the resultant capacitance. So the resultant capacitance of a parallel connected circuit or parallel capacitors, or the capacitors connected in parallel, it is given as C1 plus C2 plus C3, right? So essentially it is just the sum of the three capacitances. Now C1 is, one of them should be C1, so let's say this is C1, it is 125 microfarads, C2 is 200 microfarads and C3 is 50 microfarads. So they all are in the same unit. So probably we don't need to convert the units. So we can directly add them together. So 125 plus 200 plus 50. Altogether this should come out to be 375 microfarads. So one thing to note, since we have not converted the units, the final answer will also be in the same unit. Okay, microfarads. Right. So if we have to complicate this problem, uh, we would what we could do is we could take a capacitor of a different unit. So make sure that you have either the same unit for all the capacitors or you have converted the units, right? So essentially the values of all the capacitor should have a common unit. Okay. Now moving on to the next question. This is a question for series connected capacitors. So as we know, if the capacitors they are connected in series, we can use this formula here. Okay. So again, if we note the values of the individual capacitances, they are in microfarads. C1 is 0.1 microfarads, C2 is 0.47 microfarads, and C3 is 0.22 microfarads. So all the capacitances, they have the same or a common unit. So probably we don't have to convert the units here. Okay, so let's look at the solution of this question. So I already know the formula for series connected uh, capacitors, and I have simply substituted the values which were given for C1, C2 and C3 in the formula, and I have carefully calculated the final answer. So 1 over C it comes out to be 16.67 microfarads. Now this is not the answer, it is inverse of your capacitance, the equivalent capacitance which you are required to calculate. So don't forget to take the inverse of this value here. Okay. So if we take inverse of or 1 divided by 16.67, we will end up getting 0.06 microfarads. So again, since we have not converted the units, they were in the same unit, all the three capacitances. So my final answer is also in microfarads or in the same unit. Again, if we need to complicate this problem, maybe we could change one of the units to millifarads or something, or picofarads, right? So in that case, you will have to convert all the three capacitances to a common unit. Okay, so don't forget to take the inverse and don't forget to convert the units or keep the units same. Okay. Now, an extension of the previous question, we have it here. So in the next part of the previous question, we have to calculate the total charge flowing in the series network. Okay, we have to calculate the total charge. So since this is all the three capacitors, they are connected in series, so same charge will flow through C1, C2 and C3, as there are no other branches through which the charge or the current can flow through. It has only this path here, right? There are no other path. So the charge essentially has to flow through C2, and after flowing through C2 it will flow through C3. There is no other way the charge can go, right? So essentially in this circuit the charge will be that will be flowing is the same charge Q. So we need to find this value of Q. We already have the formula. The charge is your the total charge flowing in this circuit will be your total capacitance multiplied by the supply voltage. So in the previous part, we have calculated the total capacitance or the resultant capacitance or the equivalent capacitance, whatever you want to call it, right? That comes out to be 0.06 microfarad. So the total capacitance is 0.06 microfarads and the supply voltage Vs is 25 volt. So as you can see, the capacitance is in microfarad and the voltage is in volt. So we have to convert the unit, okay, before applying the values in the formula. So let's look at the solution of this question. So as I mentioned, the first step would be to convert the unit. So I have converted microfarads into farads by multiplying 0.06 with 10 to the power minus 6. Okay, and the supply voltage is given as 25 volt. We have both the values. We have done the unit conversion. Now they are in common units. Okay, and if we substitute the two values and do the calculation, we'll end up getting 1.5 multiplied by 10 to the power minus 6 coulombs, right? And 10 to the power minus 6 coulomb is microcoulombs, right? So it can be written as 1.5 microcoulombs. Okay. Now, in the next part of this question, we have to calculate the voltage across each capacitor, right? That is V1, which is across C1, V2, which is across C2, and V3, which is across capacitor C3. Now, as I have mentioned, since the three capacitors, they are connected in series, so the charge flowing through each of these capacitors will be the same, and it will be equal to your total charge, which we have just calculated. Okay, and we already have the formula, and if we modify the previous formula which we were using to calculate the voltage, we'll end up getting voltage is equal to charge divided by capacitance. We have already calculated the charge and we know the individual capacitances. C1 is 0.1, C2 is 0.47 and C3 is 0.22 microfarads. So we can substitute one at a time and calculate the values of V1, V2 and V3. Okay. So let's look at the solution here. So we have already seen the formula. Okay. So to calculate V1, the formula will be Q, because charge flowing through each of the capacitor is same, Q, and we have already calculated this charge Q, which is 1.5 microcoulombs. Okay. So V1, that is the voltage across capacitor C1, it will be Q divided by C1. So Q is 1.5 microcoulombs, and capacitor C1, I'm not converting the units because they both are in micro. Okay, charge is in microcoulombs, and the capacitance, they are in microfarads. Okay, so 1.5 divided by C1 is 0.1, so we'll end up getting 15 volts. Similarly, if we calculate V2, it will be charge Q divided by C2. So charge is 1.5 microcoulombs divided by C2. So C2 is given as 0.47 microfarads. I substituted it here. And after calculation, we'll end up getting 3.2 volts. And C3 is, it will be, in the same manner, it will be Q divided by C3. Okay. Charge Q is 15 microcoulombs and C3 is given as 0.22 microfarads. So if we divide them, we'll end up getting 6.8 volts. Now there is a verification method which we can use to verify our answers for this part. So according to KVL, the supply voltage should be equal to the sum of voltage drop across the components. So the sum of these voltages which we have just calculated, V1, V2 and V3, it should be equal to the supply voltage. So we are given with the supply voltage 25 volt. As per our calculation, V1 comes out to be 15 volt. V2 is 3.2 and V3 is 6.8. So if we add them together, we end up getting 25, which is equal to the supply voltage. So therefore, my answer or the voltage drops which we have just calculated, they are correct. Okay. Now let's complicate this problem a little bit here and combine the series and the parallel circuit together. So in this problem we have to so let's read the problem first. So problem number 5, it says that if a steady state DC voltage of 120 volt, and there is a little bit of mistake here. So in the question it is given as 120 volt is the supply or the applied voltage, but in the figure we have taken it as 25 volt. So let's consider it as 25 volt. So let's say if a steady state DC voltage of 25 volt is applied to the capacitor network shown below for sufficient time to fully charge the capacitor. Now we have to calculate part A, the resultant capacitance, part B is the total charge, part C is the voltage drop V2 across capacitor C2. Okay, so this voltage drop V2, and part D is electric charge Q6 of capacitor C6. So basically let's say Q6 is flowing through capacitor C6, so we have to find that value as well. So let's take one part at a time. So let's start with part A. So first of all we have to find the resultant capacitance. Now we have already seen the formula for calculating the resultant capacitance of series circuit and parallel circuit, right, individually. Now in this question we have to combine both the concepts. So first step would be to identify which of the capacitors they are connected in series. Okay, let's find series connected capacitor. So for that, what I prefer to do is I trace the flow of current or flow of charge. Okay, so let's say some charge Q, it started from the supply voltage and it starts to flow towards the left hand side, right, and again charge Q will flow in this branch, and then through C1 charge Q will flow, and then since you do not have any other alternate path, so after flowing through C1 the charge has to flow through C2. So the same charge will flow through C2. Okay, so the first thing or the first pair of capacitors which are connected in series are C1 and C2. Okay, because as per the tracing which we were doing, we could see that the same amount of charge is flowing through both the capacitor C1 and C2. right? So they are connected in series. Now let's say at this junction, so after flowing through C2, the charge Q will come out from here, okay? But at this junction, what will happen is you have two paths. One is this side and the other is this side, right? You have two alternate ways in which the charge can flow. So at junction J1, the charge Q will get divided in two parts, right? So let's say charge Q1 will flow in this path, and charge Q2, or yeah, let's say charge Q2 will flow in this path, okay? For the time being, let's forget about this Q6, okay? Um, so charge Q1 is flowing in this direction or in this path, and charge Q2 is flowing in this direction like that, okay? So the total charge is getting split up into two parts. So Q1 will flow through capacitor C3, and since after C3 there is no alternate path, so the charge Q1 has to flow through capacitor C4, okay? So the next pair of series connected capacitor which I could see is C3 and C4. They are connected in series, okay? Now Q2 is flowing in the other path, okay, in this direction. So Q2 will flow through C5, and after C5 there is again no alternate path for the charge to flow, so it has to flow through C6 as well. So again the third pair of capacitors or series connected capacitor which I could find is C5 and C6, okay? So using the formula of series connected capacitor, I will find the equivalent capacitors for each of these pair, right? So step 2 for solving or finding the equivalent capacitance would be to find the equivalent capacitance of the series connected capacitor pair. Okay, so I will use the formula to calculate, let's say, the equivalent capacitance for C1 and C2. I'm calling it as C12, okay? And the equivalent capacitance for C3 and C4, I can use the formula, it will be C34, and I'm calling this as C5/6. Okay, so let's look at the values or the calculations. Okay, so C1 and C2, they were connected in series. So I've used the formula for series connected capacitors and simply substituted the value of C1 and C2 and done the calculation, right? So after calculating 1 divided by C12 or its equivalent capacitance, I have to take the inverse. Don't forget to take the inverse. Okay, so essentially I'll be left with the final value or the equivalent capacitance. It will come out to be 15 microfarads, right? So 15 microfarads is the equivalent capacitance of the series connected capacitors C1 and C2. Similarly, C3 and C4, they were also connected in series. Okay, C3 and C4, right? So again, I have used the formula for calculating the equivalent capacitance of series connected capacitors, and I've substituted the value of C3 and C4 and done the calculations and taken the inverse. So after this step, take inverse. Okay, because this value, it is 1 divided by C34, and C34 is the equivalent capacitance of C3 and C4, which are connected in series. Okay, so if I take the inverse, I will end up getting 2 microfarads, right? And similarly, I have calculated the value for so again, C5 and C6, they were connected in series. Yeah. So C5 and C6, they were also connected in series. So again, I've used the same formula, right? Substituted the value of C5 and C6, done the calculation, taken the inverse, and finally I get this answer. So it comes out to be 8 microfarads, right? So these are the two first steps for calculating the equivalent. Now there are a few more steps. So after we have calculated the equivalent capacitances for the series connected capacitor pairs, so what I usually do is I make a fresh figure or an equivalent circuit diagram, replacing the capacitors. So I have already calculated the equivalent value for C1 and C2. So I substitute or replace the two capacitor by a single capacitor of its equivalent value. Okay. Similarly, I have calculated C3 and C4, the equivalent value. So I replaced the two capacitors by its equivalent value, C34. And finally, I have also calculated C5 and C6. Right? So I replace the two capacitors by its equivalent value. So using this, I develop an equivalent circuit diagram. Okay. Now again, if you trace the flow of charge or flow of current in this new or equivalent circuit, what we can see is now our aim will be to find the parallel connected components, right? So again, if we start tracing the flow of charge, so let's say charge Q was flowing out from the supply voltage, so it will flow through the branch here, and then it will also flow into the next branch, and then finally it will reach C12. So charge Q will flow through C12 and it will come out at this point. So again at junction, let's say this junction, again we have two paths in which the charge or the current can flow, right? So in this case, when different charge or different current flows through the component, they are said to be connected in parallel. Okay, so at this junction, let's call this as J1 again, no problem with that, right? So at this junction J1, the charge Q is getting divided into two paths, Q1 and Q2. So Q1 charge is flowing through C34 and Q2 charge is flowing through C56, right? So C34 and C56, they are connected in parallel because different amount of charge or different amount of current will flow through them. Okay, so step, I think this is third or fourth step, let's call this as step 3, is to find the parallel connected capacitors from the equivalent circuit. Okay, so C34 and C56, they are connected in parallel because different amount of charge is flowing through them, right? So again, I will find the equivalent capacitance using the formula. We have already studied the formula of um, equivalent capacitance when the capacitor, they are connected in parallel. Okay, it is simply the sum of the individual capacitances. So the equivalent capacitance of C34 and C56, I am calling it as C3-6, from 3 capacitor C3 to C6. Okay, the equivalent capacitance, okay, of all the 4 capacitors. It will come out to be, or we can use the formula, it is simply the sum of the individual capacitance C34 and C56. We have already calculated the values. C34 is 2 microfarads and C56 is 8 microfarads. So if we add them together, we'll end up getting C3-6, which is the equivalent capacitance of all the 4 capacitor from C3 to C6. It comes out to be 10 microfarads. Okay. So again, the next step would be to redraw the equivalent circuit. Okay, so basically in this method, our aim is to reduce the circuit, right, at every step. We find the components which we can combine together or which we can find the equivalent value and replace it in the circuit diagram to reduce the circuit diagram. Okay, so again, since we have calculated the equivalent capacitance for all the 4 capacitors C3 to C6, right, and so we have replaced all these 4 capacitors in the equivalent circuit by its resultant or the equivalent value, 10 microfarads. We have just now calculated that value. Okay, and previously we have also calculated the equivalent capacitance of C1 and C2, which are connected in series. Okay, so if we replace them, it is quite obvious now. If you want, you can trace the flow of charge. Basically, there is only a single path in which the charge can flow. So obviously, if Q charge is flowing from the supply voltage, the same charge Q will flow through C12 and C36. Okay, so we can say, because the same charge is flowing through both the equivalent capacitances, so they are connected in series. So I have mentioned it here. C12 and C36, they are connected in series. Okay, and again, the last step would be to find the resultant capacitance. So we know the formula. 1 over C is equal to 1 over C12 plus 1 over C3-6. Right? We have already calculated the value. C12 is 15 microfarads and C36 is 10 microfarads. 3-6 is 10 microfarads. So if we do the calculation, take the inverse here, the value whatever we are getting, we'll end up getting the resultant capacitance of the entire circuit or the given circuit as 6 microfarads. Okay, so this is the answer for part A. Now let's move on to part B, which is the total charge. We have to calculate the total charge Q on the network. Right. Now, to calculate charge, we have already discussed this formula. Charge is equal to capacitance multiplied by voltage or the supply voltage. And we have to calculate the total charge flowing in the circuit. So, if we consider the total capacitance multiplied by the supply voltage, if you notice, we have already calculated all the values, or we have all the values here. We have just now calculated the resultant capacitance or the total capacitance as 6 microfarads. The supply voltage is given as 25 volts. Okay, so we can substitute both these values in the formula, and if we do that and do the calculations carefully, we'll end up getting 150 multiplied by 10 to the power minus 6 coulombs, or we can say it is 150 microcoulombs. So that was part B. Now part C. In part C, we have to calculate the voltage drop V2 across capacitor C2. So for this part of the question, we will consider the given circuit, right? The main circuit which is given in the question. And what we can do is we can trace the flow of charge. Okay. So if you see, let's say charge Q, it started to flow from the supply voltage. So this charge Q will come out from here, it will start or continue to flow because there is no other path in which the charge can flow. So ultimately it will have to flow through capacitor C1. Okay, and after flowing through C1, it will continue to flow through C2. There is again no alternate path in which this charge can flow. So charge Q, the same charge Q which came out from the supply voltage, has to flow through C2. Okay. So basically we have found the value of charge which is flowing through C2. Okay. And in this question we have to find the voltage drop across capacitor C2. So we know the charge, the total charge we have already calculated. It is 150 microcoulombs, and the capacitance C2 is also known. So C2 is 20 microfarads. So again, using this formula, we can calculate the value of V2 or the voltage drop across capacitor C2. So if we modify this equation, we will get V2 is equal to total charge Q divided by C2. We have both the values, right? And if we substitute them in the formula here, we'll end up getting 7.5 volts. Right? So 7.5 volt is the voltage drop V2 across your capacitor C2. Now, in the last part, or in part D, we have to calculate the electric charge Q6 of the capacitor C6. So let's find that. Capacitor C6 is here, and we have to find the charge Q6. Okay. So again, basically we have the same formula which we can use again. So this formula, Q is equal to C multiplied by V. Okay, so let me write it down. charge Q is equal to C multiplied by V. Okay, so this formula we have to use to calculate the charge Q. So we have to find Q6. So for that we have to find the value of C6, or you can say the equivalent capacitance. Now, one thing which, if you remember about parallel circuit, is the voltage drop across each of the branches. They are same. Okay. So the voltage drop, let's say VP, V parallel, they are the same. Okay. So basically our aim is to find the voltage drop across all these capacitors from 3 to 6, and the equivalent capacitance from C3 to C6 we have already calculated, and that came out to be 10 microfarads. So if we use this formula here, we should be able to find the charge Q6. Okay. So first of all, what we have done is we have already calculated the value for the voltage or the capacitance from C3 to C6, the equivalent capacitance. We have calculated that to be 10 microfarads. Now the total charge flowing in this circuit, in this parallel circuit, is 150 microcoulombs. Right? So using these two values, we will find the voltage across this capacitor. Either you can say the voltage drop across C5 and C6, or we can say the voltage drop across C3 and C4. They will be the same because they are connected in parallel. Okay. So using this formula, first we calculate that voltage drop. Okay. So V3-6, as I have mentioned, it comes out to be Q, the charge Q which is flowing, divided by C3-6, the equivalent capacitance. Substitute these two values which you have already calculated, and if you do the calculations properly, you should end up getting 15 volts. Okay, so we have calculated this voltage drop across C5 and C6. Mainly we are concerned with C6 here. Okay, C5 and C6. Okay, so we have calculated this voltage. Now C5 and C6, they are connected in series. So its equivalent capacitance we have already calculated in the first part. It came out to be 8 microfarads. Okay, so now we have the voltage drop across this capacitor and the equivalent capacitance. Right? So we can use these two values to calculate the charge which is flowing through C6, and just to note, the same charge will flow through C5 and C6, both of them. That is why we are considering the equivalent capacitance. They are connected in series, so the same charge will flow through both of them. Okay. So even if you consider the equivalent capacitance, C5 and C6, it will make no difference because same charge is flowing through both of them. And we are also taking the voltage drop across both the capacitors. Right? C36 is this from here. It is the voltage drop between C5 and C6, or across C5 and C6. Okay. So we are considering both the capacitors together because same charge is flowing through both of them. Okay. So we have already found the values. If you substitute it here, you should end up getting 120 microfarads. Now, the last topic which we have to study in this course or in this lecture is effect or the factors affecting the capacitances, or the factors affecting the value of capacitance. Now basically the value of capacitance or is affected by these three factors. So the capacitance, it depends on the area of plate, right? And it depends on the distance between the two plates, and it depends on the permittivity of the dielectric medium between them. So we have seen this diagram before. So capacitor, essentially it has two parallel conducting plates which are separated by a dielectric medium between them. Okay? So it depends on the area of cross section of these plates, and it depends on the distance between the two plates, and it also depends on the permittivity of dielectric medium. Now permittivity epsilon, it is equal to epsilon naught multiplied by epsilon r. So epsilon naught is the permittivity of free space, and it has a fixed value 8.85 multiplied by 10 to the power minus 12. Okay, and epsilon r is the relative permittivity, right, in respect of free space. So essentially you can see the permittivity values, they are quite quite complex to remember. Something like 8.85 multiplied by 10 to the power minus 12, right? And similarly, if you have permittivity of mica or permittivity of water, right? So like that, they will have these decimal values which are quite complex to remember. So what we have done is we have developed a relative or permittivity. So relative permittivity would be something like 1.5 times the permittivity of free space. In respect of the free space, what is the permittivity of a certain material? That is your relative permittivity, right? So maybe something like permittivity of oil, it is 2.1 to 2.4, which is quite easy to remember in comparison to a very long decimal value, right? So that is why we use relative permittivity. And your overall permittivity of any medium, it is epsilon naught, which is permittivity of free space, multiplied by the relative permittivity. Okay. So the value of capacitance C, since it depends on the area of cross section, it depends on the permittivity of the medium and the distance, right? So using this relation, we can develop a formula for capacitance. So capacitance C is directly proportional to the permittivity of dielectric medium. It is also directly proportional to the area of cross section. So if you have larger area of cross section of the plates, your capacitance will be larger. Similarly, if your dielectric medium is a very large value. Sorry, a dielectric medium, it has a high permittivity. In that case, the capacitance will be very small. Sorry, very large. And capacitance C is inversely proportional to the distance between the two parallel plates. So as I mentioned, if you reduce the distance between the two parallel plates, the capacitance will increase, right? So combining these relations, we can develop a formula for capacitance, another formula for capacitance. So capacitance is epsilon naught, which is permittivity of free space, multiplied by epsilon r, which is relative permittivity of the medium, multiplied by the area of cross section, divided by the distance between the two plates. Now based on this formula, let's take a question. So this question asks us to calculate the capacitance of a capacitor having two parallel plates with a mica dielectric. So the dielectric medium between the two parallel plates is mica. Okay, something like this you have. This dielectric medium is mica. Okay. Of relative permittivity of 5. So epsilon r is given as 5 between them. The plate cross-section area, so the cross-section area of the two parallel plates, it is given as 500 millimeter square, and the distance between the two parallel plates is given as 0.3 millimeters. Now permittivity of free space, it is 8.85 multiplied by 10 to the power minus 12. So epsilon naught is 8.85 multiplied by 10 to the power minus 12 farads per meter. Epsilon r, it has no units. Okay. Now it is a relative value. Epsilon r is a relative value, so therefore it doesn't have any units. Now in this formula we have all the values from the question, right? The only thing is to consider the unit. Area is given in millimeters square, distance is again given in millimeters, but epsilon naught is farads per meter, so we will have to convert the unit. So let's look at the solution of this question. So epsilon naught is 8.85 farads multiplied by 10 to the power minus 12 farads per meter. Epsilon r, it doesn't have any unit, so no problem with that. Now area is given as 500 millimeter square. Now 1 millimeter is 10 to the power minus 3 meter. So 1 millimeter square will be 10, again if you multiply it by 10 to the power minus 3 meter square, like that. So altogether it will be 10 to the power minus 6 meter square. So if I convert 500 millimeter square, I'll have to multiply it with 10 to the power minus 6 to convert it into meter square. Okay. So I've done that. Now the distance between the two parallel plates is given as 0.3 millimeter. If I convert it into meters, I'll have to multiply it with 10 to the power minus 3. So now I have converted all the units, and all the units are same, right? So now I can use the formula and simply substitute the values and do the calculations correctly. You can use your calculator. So this calculation you have to do it a bit carefully. They have lots of 10 to the powers, right? so do it carefully. But finally, you should end up getting 73,750 multiplied by 10 to the power minus 15 farads, or we can write it down in a simpler form as 737.5 picofarads. So this will be your answer, right? So this is all about all the things which we have to discuss in this topic of capacitance. So thank you very much and see you in the next class.